Good evening, Lamai. Today we are going to discuss about the enthalpy change of combustion. Right? That is the third enthalpy term we are going to study. First, let's come up with the definition. Right? First write the definition, Lamai. Then we'll discuss that thing further. So just come up with the definition. So at the space given there. Right? Just write the definition here. Come to the red color pen and write the definition. Right? Enthalpy change when one mole of an element / compound, enthalpy change when 1 mole of an element / compound in the standard state undergoes complete combustion with excess O2 gas, undergoes complete combustion with excess O2 gas, within brackets O may say air, close the brackets, in the standard state give the products within brackets, just write respective oxides, close the brackets, in the standard state. So just box the definition, right? And then underline this, or you can highlight the most important stuff there. So when it comes to a thermochemical definition, right, the most important two things are, the first thing is where the 1 mole stands, and the second thing, what are the components at the other side of the equation. So chemical reaction is with two sides, no? Reactants and the products. No? At one side, the species with 1 mole will stand. What are the things at the other side of the reaction? That is also should be known. Right? Those are the most two things, important stuff when studying about a thermochemical expression. Right? So just underline or highlight these stuff in your definition. First, where the 1 mole stands, right? So underline or highlight this phrase, 1 mole of an element / compound. 1 mole of an element / compound. Highlight this stuff, right? That is where the 1 mole should stand with the respective compound of the element, which is we are trying to combust, right? So then what are the things at the other side? Give the products within brackets respective oxides. Give the products within brackets respective oxides. Just highlight that stuff as well, right? So that those are the things at the other side of the equation, right? So this is the definition. So let's come up with some examples, right? Some examples to correctly understand this scenario, right? So I'll come up with the examples given in your tube, right? So 2 examples are given. What are those, right? The first example we are going to study here is the standard enthalpy change of combustion of carbon solid graphite. Combustion of carbon solid graphite is given as minus 393 kilojoules per mole. So let's come up with the thermochemical reaction for this one. So where the 1 mole stands? This is all about the combustion of carbon solid graphite. This is all about the combustion of carbon solid graphite. So 1 mole should stand there, right? So carbon solid graphite, that is the one to start with the species where the 1 mole appears, right? The combustion means reacting with O2. Combustion means the reacting with O2, reacting with excess O2 gas to produce what? To produce products at the standard state. What are the products at the standard states? The respective oxides. To produce the respective oxides at the standard state, right? So the oxide of carbon, the most stable oxide of carbon is what? That is CO2. CO2. So you are supposed to come up with the most stable oxides of the atoms, right? Most stable oxides of the respective atoms of your considering 1 mole species, right? So this is the respective oxide, right? So that is considered as a stable oxide, right? Right. So then we have to balance this stuff. So as 1 mole stands here, just one mole of carbon should be there. So only one here. So the thing is balanced, right? So this enthalpy change is given as minus 393 kilojoules per mole. Right now, the thing is clear. Let's come up with another example. The second example appearing in your note. That is all about the magnesium's combustion. Right? Standard enthalpy change of magnesium solid. Change of combustion of magnesium solid. Is given as minus 602 kilojoules per mole. Let's come up with the thermal equation for this thing. So 1 mole should stand with magnesium solid, the species to combust. So magnesium solid is the species to combust, and combustion means reacting with O2 gas, right? 1 mole appears here. The species we are combusting, right? So have to come up with now, come up with the respective oxides of the considering elements, right? Elements of the 1 mole species, right? So magnesium's oxide, the stable oxide is the magnesium oxide, which will appear like this. It appears as a solid. All the metal oxides will appear as solids. Non-metal oxides may appear as gases or liquids. Non-metal oxide, the CO2, carbon oxide, it's a gas. SO2, sulfur oxide, it's a gas. NO2, nitrogen oxide, it's a gas. H2O, the hydrogen oxide, it's a liquid, right? So non-metal oxides normally appears as liquids or gases. Basically, when you can form the hydrogen bonds, then appears as liquids. Other than those situations, normally non-metal oxides are considered as gases at atmospheric normal conditions. But the metallic oxides are always solids. Magnesium oxide, zinc oxide, sodium oxide, potassium oxides, aluminium oxides, all the metallic oxides, as those are bound, the particles are bound with ionic bonds, strong ionic bonds, those are solids, right? The ideas are clear now, right? Okay, so the products are written. Now we need to balance this stuff. As this thing should be 1 mole, you have 1 magnesium atom at the left hand side, so at the right hand side as well should have only 1 magnesium atom, so this should be 1. So when balancing oxygen, you have just 1 oxygen at the right hand side, so that here the value should be half of O2, no? Half of O2 will give you 1 oxygen atom. Right now, balancing is done. So this enthalpy change, this change needs minus 602 kilojoules per moles of energy change, right? Now this amount of energy change required to convert this state to this state. To do this state change, you need to do this kind of energy change, right? Thing is clear, right? Third one, let's come up with the third one appearing in your note. It is about the combustion of CH3OH liquid, no? So that is standard enthalpy change of combustion of right CH3OH liquid. So this is a polyatomic species. Is given as what? What is the number there? -726 kilojoules per mole. Let's come up with the correct thermochemical equation for this one, right? So the 1 mole species, this is all about the combustion of CH3OH liquid. So 1 mole species is CH3OH liquid. That is where the 1 mole stands, right? Then combustion means reacting with O2 gas. Reacting with O2 gas. Right? So, what are going to be the products? What are going to be the products? The products are going to be the respective oxides of the constituent elements of the 1 mole species. Right? So, you are with carbon, hydrogen. The carbon's oxide is CO2. Hydrogen's stable oxide at room conditions is the H2O. Hydrogen connecting with oxygen to form the H2O. Carbon connecting with oxygen to form the CO2. So we are not writing anything as the oxide of oxygen, right? So CO2 and the H2O are the products, right? So CO2 gas and H2O gas are the respective oxides. So H2O liquid, sorry for that, H2O liquid, right? So the form which is stable at room conditions, right? Stable oxides. So the stable oxide. Right? Now we need to balance this stuff. 1 carbon appearing, that means just 1 carbon should be there as well. And 4 hydrogens are appearing. So to give 4 hydrogens, you need 2 here. Right? And altogether 2 oxygens are appearing. 2 and 2, another 4 oxygens are appearing at the right hand side. As you have 1 oxygen here, this should represent 3 oxygens. As altogether 4 oxygens should be there. 1 is here. So this term should represent 3 oxygens. To represent 3 oxygens, you have to come up with like this, no? 3 over 2. So those will cancel off to give you the 3 oxygens, right? So that is how we are supposed to balance. We are supposed to do the mass balancing with this equation, right? So the energy change involved when changing this state to here is actually minus 726 kilojoules per mole. Right? Things are clear? Right. And always keep that in mind, Lamai. All the combustion enthalpies are referred to as exothermic values. Even with these examples, you clearly see all the combustions are exothermic. Right? If you combust the carbon, it's an exothermic reaction. If you combust the magnesium, it's an exothermic reaction. If you combust the methanol, CH3OH, it's an exothermic reaction, right? If you combust anything, if you combust this marker pen, it is kind of a exothermic reaction, right? If you combust this board, yes, it's an exothermic reaction. Combustion of anything is referred to as an exothermic reaction, right? Okay, always the enthalpy changes are coming up with some minus values, right? Okay, So just complete this stuff, right? After writing these things, right, you can do the exercise at your tute, right? So it's clear now? Right, let's do the exercise which is appearing in your tute, right? So at the page number 20 of your tute, it is said that write the thermochemical reactions for the enthalpy changes of combustions of substances given below. Let's try to do that work, right? Right, what are the exercises appearing in your note? Right, see, I'll add the stuff here. As number 4, they are asking you to come up with the delta note C, the combustion of C5H, sorry, C2H5, no? C2H5 OH liquid. Then number 5, it is this enthalpy change of combustion of C6H12O6. It's a solid, no? Right. Number 6, that is for standard enthalpy change of combustion of C3H8 gas. Right. Other stuff. Number 7, that is delta H naught C of CO gas. Number 8, delta H naught C combustion of H2 gas. Number 9, enthalpy change of combustion of CS2 gas. Number 10, enthalpy change of combustion of sodium solid. Right now? Okay. Let's try to write the thermochemical equations for these things. Right. Let's start with the number 4. So we are supposed to combust 1 mole of C2H5 OH liquid, right? The 1 mole stands with the species to combust, right? So let's start with that. So C2H5OH liquid, the 1 mole stands, right? You don't need to write the 1 mole thing, right? Always, right? So combustion means reacting with excess CO2 gas for a complete combustion. Is delta H naught C to produce respective oxides. What are respective oxides? The elements, component elements are the carbon and hydrogen in this case, right? Oxygen won't form the oxides, right? So carbon and hydrogen. So carbon's oxide is CO2 gas. It appears as a gas form in the normal room conditions, and the hydrogen's oxide is H2O. Appears as a liquid. So let's balance the stuff. You need 2 carbons. So that means 2 of CO2 is needed. As you are with 6 hydrogens at this side, right? You need 3 of H2Os. So let's balance the oxygens as well. So you have 4 oxygens and another 3. That means 7 oxygens at the right hand side. That means altogether 7 oxygens there should be at the left hand side as well. Here you have 1 oxygen, so this term should represent 6 oxygens to a total of 7 oxygens at this side. So that to give 6 oxygens, you need 3 of O2 gas molecules, right now. So that is how this thing is balanced. Let's copy this one. So the 1 mole species is this thing, that is the species to combust, right? So C6H12O6 solid is the one to combust. Combustion means reacting with O2 gas, right? So when combusting this thing, you will produce carbon dioxide and the H2O, right, as the oxides of the constituent elements, H2O liquid, right? So now we need to balance the stuff. When balancing, you need 6 carbons, so you need 6 here, needs 12 hydrogens, that means need some 6 here, that will provide you 12 hydrogens. So balancing the oxygens now, 12 here and 6 here, altogether 18 oxygens should be there at the left hand side as well, because the 18 oxygens are there at the right hand side, right? So this guy will represent 6 oxygens, so that this term should represent altogether 12 oxygens to give a total of 18 oxygens at this side, right? So that you should compute some 6 here, that will give you 12 oxygens, and this 6 will add up to give you 18 oxygens. So oxygens are balanced, right? So that is how things are balanced here, right? Next one. So species to combust is this one. This is the 1 mole species then, right? So C3H8. It's a gas. Combustion means reacting with O2 gas. It's all about combustion enthalpy of this one, right? So what are the products to form? So you have to produce carbon oxide, carbon dioxide and hydrogen oxide, that is H2O liquid, right? So it's carbon dioxide will be appears as a gas, and hydrogen oxide appears as a liquid at room conditions, right? So let's balance 3 carbons and 8 hydrogens, that means 3 here, 4 here to provide 8 hydrogens, right? Then balancing the oxygens, you have 6 oxygens and 4 means 10 oxygens are there. There are no oxygens here, so all the 10 should be represented by this term. So need to come up with 5 O2 gas molecules to represent 10 oxygens at the left hand side as well. So that is the balanced thermochemical reaction for combustion of C3H8 gas, right now. Okay, let's come up with this one, right? Combustion of carbon monoxide. See, so carbon monoxide, that is the species to combust, so that is the one to appear with 1 mole situation. Combustion means reacting with O2 gas, right? Then what are the products? So carbon will react with O2 to form the carbon oxide, that is the carbon dioxide, appears as a gas at room conditions, right? And oxygen oxide is not considered, right? You are not writing the O2 in both sides, no? Oxygen oxide is actually O2, right? Okay, it won't be written because in chemical reactions you won't write the same thing at the reactant and the product sides, right? Okay, so these are the components appearing in this equation, right? Now we need to balance the stuff, right? So you are with 1 carbon, yes, 1 carbon, but with 2 oxygens here, so that you need to balance the oxygens amount at 2, right? So 2 oxygens here, this represents 1 oxygen, so this should represent only just 1 oxygen. So for that, this should come up with a half a value. Half of oxygen will provide 1 oxygen, 1 plus 1, 2 oxygens at the left as well as at the right, right now? Okay, next one, balancing of H2O gas combustion, right? So H2O gas, that is the species to combust. So H2 gas, sorry. Combustion means reacting with O2 gas to produce the respective oxides of the elements appear in there, right? So the hydrogen oxide is H2O liquid. H2 appears as a liquid at room conditions, right? So see, balancing, 2 hydrogens needed, 2 hydrogens are okay, but just 1 oxygen is needed, so it should be just 1 oxygen, so half value of O2 gas means one oxygen is representing from this term, right? That is balanced. This one, combustion of CS2 gas. So CS2 gas is the species to combust. That means the species to react with O2 gas. This is all about combustion of CS2 liquid. Sorry, CS2 gas. Right. So it was gas, no? CS2 gas, yeah. Sorry, it is given as CS2 solid. Sorry for that, right? They have given it as CS2 solid, right? In this question. So carbon oxide is CO2, appears as a gas, and sulfur oxide is SO2, which will also appear as a gas. Right, let's just balance the stuff. One carbon, okay. 2 sulfur atoms are there, so 2 is needed here. So oxygen count, 4 oxygens, 6 oxygens. So to come up with 6 oxygens at this side, you need 3 here. Right, that's the combustion of CS2 solid. The final thing, combustion of sodium solid. So sodium is the one more species, the species to combust, where the one more should appear with the combustion enthalpies, right? So that should react with O2 gas for the combustions. It's a must to react with O2 gas, right? So what will be the product? This guy is oxide. Sodium's oxide means Na2O. Exchange of valencies, Na plus and the O2 minus. Exchange of valencies, Na2O. The metal oxides will appear as solids at room conditions. Let's balance this up. You need just one sodium, right, in your system, each and every states of your system, right? So just one sodium, that means you need some half here to provide one sodium. Half into Na2, it will be one sodium. So then comes the oxygen's term, right? So half oxygen appears at the right hand side, half oxygen, right? Half of oxygen. That means you need to come up with 1/4 of O2. 1/4 of O2 will provide half of oxygens, right? This thing will cancel out half of oxygens, right? So these are the answers, right, for the question appearing in page number 20. So just complete the stuff, Lama. Just complete. Right, no? Okay. So at the page number 21, right, it started with some statement. That statement was actually all the combustions are exothermic. Remember that. I had earlier also discussed about that thing. Remember that. That is very important. All the combustions reactions are exothermic. Delta H are negative values. Right now? Remember that. Okay. Now we are moving towards the problem solving. Right, with the combustion enthalpies. When the data are appearing as combustions, right, we are going to discuss about the problem solving techniques, right? So basically, when the combustions are appearing as data, you may need to construct a thermochemical cycle to solve these questions. So equation form is not available with combustion enthalpies, right? So we need to come up with the thermochemical cycle to solve these problems when the combustion data are available, right? So let's use those combustion data to solve these questions, right? You have a question like that at the page number 21, right? So let's try to solve that one with the use of a thermochemical cycle, right? Right, this is about problem solving involving combustion enthalpies, right? Right. So, what is this first question? Right, they have asked you to find out the standard enthalpy change of formation of benzene, right? So, your question was finding out the standard enthalpy change of formation of benzene. Benzene means C6H6 liquid. This is the problem that they are asking to find out the standard enthalpy change of formation of benzene. And what are the data provided? Data provided are these delta H naught C values. Some of the delta H C values are given for carbon solid graphite as well as for H2 gas as well as for C6H6 liquid. The combustion values are given. What are those values? Minus 393, minus 286. These are kilojoules molar, right? And minus 3284. Right? Okay. Let's try to solve this one. Right? So these are the data provided. Right? And this is our task. This is our goal. This is our goal to find out the formation enthalpy of C6H6 liquid. Right? So what we are supposed to do? So I am going to solve this one with the use of a thermochemical cycle. So the first thing, what we are supposed to do? The first thing, when trying to solve a problem with the use of thermochemical cycle, the first thing to write is the thermochemical reaction related to your goal. The first thing to write is the thermochemical reaction, the balanced thermochemical reaction related to your goal. Let's start with that, right? So the goal is the formation of C6H6 liquid. Let's write that to start up with, right? So let's start with that, right? Okay. So let's F of C6H6 liquid. So this is delta H naught F of C6H6 liquid. So C6H6 liquid, that is where the 1 mole should stand. This formation of C6H6 liquid. 1 mole should stand with this compound. So it's a formation. Formation means, right? So I may need some more space now, right? Okay, I'll write it here. So it's all about formation of C6H6 liquid, right? Okay, here the 1 mole stands. So it's about a formation enthalpy, so that we need, at here we need the reference forms of these constituent elements. So you have the carbon's reference form is carbon solid graphite. We need 6 carbon atoms plus hydrogen's reference form is H2 gas, right? We need 6 hydrogens, that means 3 of H2 gas. So this is the thermochemical reaction related to the goal. First thing is to write that thing. Next, the next thing is we need to come up with this imaginary state. We need to come up with the imaginary state to build up the cycle. To build up the cycle, we need to come up with the imaginary state. Without imaginary state, without at least 3 states, you can't complete a cycle, right? You need to come up with the imaginary state here. So how to produce the imaginary state? How to come up with the imaginary state? So when writing the imaginary state, the components of the imaginary state, right? First, you need to consider the data given here. You need to consider the data given here, right? What are the data given here? Data given are the combustion data, right? So just think of what are the chemical components available with the combustion data, right? So with the combustion data, the respective species to combust as well as the respective oxides, those are the things available with the combustion data. The species to combust as well as the respective oxides. Already you have written the carbon, hydrogen, right? So the species to combust, carbon, hydrogen are written, as well as this one, CCH6, the species to combust have been written, but not the respective oxides, So your imaginary state should be built up with the respective oxides, with the missing pieces, the respective oxides, right? So let's come up with that. So your imaginary state should come up with respective oxides. So respective oxides of the elements of this system. So your system contains carbon atoms and hydrogen atoms. So the respective oxides are CO2 gas and the H2O liquid. You have to balance this stuff. As your system contains 6 carbon atoms and 6 hydrogen atoms, there should be 6 CO2 molecules and 3 of H2O liquid molecules, right? Because as a thermochemical cycle, we are representing some different states but of a same system, different states of a same closed system, right? So with all the states, the mass should be conserved, the same atoms should appear, right? So that is why this is balanced like this. 6 carbon atoms appear, so 6 of CO2 should form, 6 hydrogen atoms appear, so 3 of H2O should form by those combustions, right? Okay, the imaginary state is done. Now you need to balance the other two states as well for the mass balancing, as you are with 12 oxygens as well as 15 oxygens all together at the state of your system. All the other states of your system should also contain 15 oxygens, because this represent different states of same system. This system contains now 15 oxygens. That is what this state says, right? So you need some 15 oxygens. So applying some 15 oxygens in the form of reference state, applying 15 oxygens do nothing to your energy. So if you are applying 15 oxygens in the form of the reference state, that will do nothing, right, to your energy changes, because the reference state carries zero energy. The reference state of an element carries zero energy. So just applying 15 over O2 gas molecules just to do the mass balancing will do nothing to your energy balancing, right? So don't worry, when applying to do the mass balancing, always apply in the form of the reference state, right? So as you have added 15 over O2 gases to this equation, which is already balanced, you have to do the same thing to the other side as well. If not, balance is disturbed, right now, so that we can apply that thing like this. Clear? So now the 3 states are balanced mass wise as well. Okay, now we need to relate. Now what we need to do is just to relate the 3 states with the energy changes, needed, right? So only the combustion data are available. So combustion means the species to combust will react with excess CO2 to form the respective oxides, so that the arrows should come towards the respective oxides. The arrows should come towards the respective oxides like this, right? Let's copy the values, the changes of heat needed to convert this state of a system to this state, right? Here, actually, to come up with 6 of CO2s and 3 of H2Os, you have to combust 6 moles of, this is the 1 mole, we have this 1 mole stands now, you have to combust 6 moles of carbon solid graphite and 3 moles of H2 gas. To combust 1 mole of carbon solid graphite, you need this amount of energy change to combust 1 mole of carbon solid graphite. So now you need to combust 6 moles to convert this state to here. So 6 into the combustion of carbon solid graphite, that is minus 393 kilojoules per mole, right? Doing that change is not enough to convert totally this system to here. You have to convert this 3 of H2 gas things as well to 3 of H2O liquid, right? So to combust 1 mole of H2 gas, you need this amount of heat change, but to convert 6 moles of H2 gas, combust 6 moles of H2 gas, you need 6 times of this energy change, right? So it is going to be, 3 times of that energy change, as you need to combust for 3 moles, right? So 3 into this data, right? Combustion of H2's value, right? That is 286, right now. So if you apply this total energy change to this system, that will be converted to, right, this state of your same system, right? Okay, then let's try to combine this state to this, right? So basically it is about combustion, so definitely reacting with O2 to bring you the respective oxides, right? So here you are with just 1 mole of C6H6 liquid, so the energy change needed to combust 1 mole of the stuff is enough to combust this whole system to here, right? So that is appearing as a minus 3284 value, minus 3284 to combust 1 mole of C2H6 to give the respective oxides, right? So that is the value appearing there. If you are to do this energy change, this state of the system will totally convert to this, right? So that our enthalpy cycle is completed, thermochemical cycle is completed. So we can apply the Hayes law to this one to come up with the wanted delta H naught F. So how to apply the Hayes law? So first you need to come up with the initial and final states here. So what is the initial state and what is the final state here? So initial state is the state where all the arrows begin. So from this state, all the arrows begin. So this is your initial state, and final state is the state where all the arrows ends, right? So all the arrows coming towards this state. So this is going to be your final state, right? 2 routes are available to come from initial to final. This is one route. Other route is this. So Hayes law means if you are dealing with the same initial and final states, right, the pathway it took to come to the final state won't matter. The change in thermochemical data will be the same. So if you are coming from this route or this route, the change in enthalpy will be the same. So those are equal, right? So we can write according to Hayes law, according to Hayes' law, we can say the enthalpy change of this route, that is delta H naught F minus 3284 kilojoules per mole, that is the complete enthalpy change of this route, that will be equal to the enthalpy change of this route, right? That is what Hayes law says, right? It is going to be 6 into minus 394 23, no, plus 3 into minus 286, right? The two enthalpy differences are equal as you are dealing with same initial and final states, right? So this will give you, if you can subject the delta H naught F, right? That will give you the answer. So if I am to subject this value, it will be given as plus 68, right? Plus 68 kilojoules mole. Right? This is your answer. Right? No? This is how you are supposed to solve this kind of question with the use of a thermodynamic cycle. Right? So just complete this stuff. Right. Let's do the next question appearing at the page number 21. Right? This was the example question, right, which I have done, right? So now let's do the question number 1 appearing at the bottom part of the page number 21, right? Let's do that stuff as well, right? So first of all, what is the, this is all about page number 21, question number 1. Right, that is what I am going to do now. It is all about finding relative F value of which one? C2H5OH, no? C2H5OH liquid, no? Yes, that is needed to be found, right? And they have provided you some combustion values, no? They have provided you some combustion values, right? I'll write those values here. Right? They have provided some combustion values, so carbon solid graphite, H2 gas as well as C2H5OH liquid, right? For the carbon solid graphite, H2 gas as well as for C2H5OH liquid, the combustion values are given minus 393, minus 286, and the value for C2H5OH was given as 1372. No? Right, no? Let's try to solve this problem with the use of a thermochemical cycle. Right, with the use of a thermochemical cycle, let's try to solve this one. Right. Okay. So solving the problem with the use of a thermochemical cycle. Right. The first thing to do is actually first you need to write the thermochemical equation related to your goal. Thermochemical equation related to your goal. This is your goal. You need to come up with the formation enthalpy of C2H5OH liquid. So you need to first write the thermochemical expression, the equation, the balanced thermochemical equation related to this goal, right? That is the first thing to do, right? Okay, let's start with that. So this is all about coming up with the delta H naught F of C2H5OH liquid, right? C2H5OH liquid, right? So this is the other one more stance. So you need to come up with the reference forms of respective elements here, right? For as the enthalpy change is kind of a formation, right? So carbon's reference form is carbon solid graphite. Such 2 carbons should appear, right? Hydrogen's reference form is H2 gas. Such 6 hydrogens should appear. That means 3 of H2 gas. And oxygen's reference form is O2 gas. Such 1 oxygen should appear. That means just half of O2 gas. So starting from the reference forms, you need to come up with the C2H5OH liquid. That is the enthalpy change we are looking for, right? Okay, this is your goal. First come up with the goal. Next thing is to come up with an imaginary state. Come up with an imaginary state to complete the cycle. So you need at least 3 states of the same system to complete a cycle, right? Okay, how to write the components of this imaginary state? Just look at the data given. Just look at the data given. Yes, the data given are all about combustion data. Combustion data. So combustion data involves, the major stuff with the combustion data are the species to combust as well as the respective oxides. Respective oxides. So one more stands with the species to combust, and respective oxides are the ones at the other side, right? Those are the special things when regarding the combustion data. So then look at your diagram and see what are the things which are not already written. So the species to combust are already written. Species to combust, carbon, hydrogen as well as C2H5OH liquid. The species to combust already written, but you haven't written the oxide set. You haven't written the oxide set, right? Species to combust, and the at the other side the oxide should be there for the combustion data, right? So respective oxides are not written with this system, so that we need to come up with the respective oxides at the imaginary state, right? So let's build up the imaginary state in terms of respective oxides, right? Okay, so this system contains 2 carbon atoms, 6 hydrogen atoms, and some 1 oxygen atom. So if you think of the respective oxide, the carbon's oxide is going to be CO2 gas. As 2 carbon atoms are appearing, 2 of CO2 should be formed, and hydrogen's respective oxide is the H2O liquid. H2O liquid, right? So as 6 hydrogen atoms appearing at your system, so it should be 3 of H2O liquid, right now? So these are the respective oxides. Now we have to consider the mass balancing of the 3 states. As when we are writing the oxides, the amount of oxygens may change. So if it is happened like that, we have to balance the mass again as well, right? So altogether you have 4 oxygens here, 3 oxygens here, altogether 7 oxygens are written with the imaginary state. So all the other states should also have some 7 oxygens as well. So mass should be balanced because we are dealing with the same closed system. Even though the states are different, these are all about same closed system, right? So 7 oxygens should appear with all these states, right? Still we have written only 1 oxide. So that we need to write another 6 oxides, 6 oxygens to these states, right? So we can come up with 6 oxygens as 3 of O2 gas. Always add those elements with the reference form, right? So that you are doing nothing to the energy there. Energy balance is not harmed, right? If you are adding the things, right, with the reference form of those elements, right? So now the 7 oxygens have been supplied for this state as well. So for this state also you need, so if you have done some change to all reaction already balanced, you need some 3 of O2 gas to this side as well. So this 3 of O2 gas and this thing all together, it will going to be 3.5 moles of O2 gas. That will be, can be written as, represented as 7 by 2 O2 gas, 7 by 2 O2 gas, right? We are not writing the O2 into right spaces, right? So just add that 3 of O2 gas and half of O2 gas to write as 7 O2 O2 gas, right? So this will also represent 7 oxygen atoms. So 3 states are completed. Now our task is to connect these 3 states, right, with the energy changes, right? Okay. So when thinking of the right directions of the arrows, right, basically in combustion, as the combustion data are given, in combustion the arrows will be headed towards the oxides. You are starting with the compounds to combust or the elements to combust, and arrows will be headed to respective oxides. So arrows should be written towards the oxides, right, as combustion data are provided. Even here the arrows should be written to the oxide, right? Okay, let's come up with this energy change. So here you have 2 moles of carbon solid graphite. To combust 1 mole of carbon solid graphite, you need the enthalpy change of combustion of the carbon solid graphite, that is minus 393. Now you have to combust 2 moles of such, right? So 2 into minus 393 kilojoules per mole. That will convert all the carbons to CO2 gas. And you have 3 moles of H2O gas here also to combust, to provide the 3 moles of H2O liquid, right? So to combust 1 mole of H2 gas, you need minus 286 kilojoules of heat. So now you need to combust 3 moles. So 3 into the minus 286 kilojoules per mole. So if you apply this total energy change, this state of your system will totally convert to this state of the system, right? So that change can be done by applying this energy change. Then converting this to here, right? So here you are just with only 1 mole. So this is all about converting this 1 mole to combusting this 1 mole of C2H5OH to respective oxides, right? So to combust 1 mole of C2H5OH, you need this amount of energy change, minus 1372, minus 1372. So if you are to apply this energy change to this state of the system, that will be totally convert to the respective oxides, as it's a kind of a combustion enthalpy, right? Okay, so this is our cycle, the completed cycle. Now we can apply the Hayes' law to come up with the needed delta H naught F, right? To apply the Hayes' law, first you need to come up with the initial and final states, right? So initial state is the state where all arrows begin. So this is going to be the initial state here. All arrows begin from there. And final state is the state where all arrows come in towards, right? So this is the final state then. As you clearly see, all of these arrows come in towards this state. This is going to be an intermediate state, right? So the 2 routes available to come to the final state starting from the initial state are these 2. This is one route and this is the other one. So the enthalpy changes with those should be equal according to Hayes' law, right? So the enthalpy change associated with the first route is actually delta H naught F plus this, delta H naught F plus this value, that is 1372. That is going to be equal to the total enthalpy change, right, happens with the second route, that is Hayes' law, right? 2 into minus 393 plus 3 into minus 286. That is the total enthalpy change happen when you are coming from initial state to final state by the second rule, right? So by solving this, you can come up with the delta H naught F value. Let's try to solve this one, right? The second one. Okay, so you can just copy the stuff Lamai while I am simplifying these things, right? I'll use the calculator, right? So the values, no? So this thing will come to this side, right? Minus these values, no? 2 into 393. Another minus value appearing from here. 3 into 286. That's going to be minus 272, no? The value will be minus 272. Right now? Okay, this is the H naught F value, right? Let's complete the stuff now. This is the question number 1 appearing in your page number 25 of your tutor, right? Okay, let's complete the stuff. You have some space to write at the page number 22. You can use that space to complete this stuff. Right now, okay, let's try to do the question number 2 as well, appearing at the page number 22. See, that's a good question, right? See how we are supposed to solve that thing. Just try the question at the page number 22. Right, just do the question number while I am writing the data here. Data provided is the question number 2 at the page 22, right? See what they are saying. So some data are provided, and what was the goal? The goal was to find out the change of formation of sulfuric acid, right? So it should be H2SO4 liquid, right? H2SO4 liquid. So the goal is to find the F value formation of sulfuric acid, right? H2SO4 liquid. That is your goal, right? That is your goal. So what are the data provided? The data provided are, right, these things. The electron C values are given for sulfur, solid rhombic. That is the reference form of sulfur, right? And electron C value is given for H2 gas as well, right? The two values are minus 298 kilojoules per mole, and the other value is minus 286 kilojoules per mole, right? So some data are given as equations as well, right? These are another two data given, right? Some changes of reactions are given. Then 2 of SO2, it should come up with the physical as well, right? Just put these gas things, right? Plus O2 gas. When those convert to 2 of SO3 gas, the value is given as, right? I'll write that thing on top of the arrow, right? Then it is easy to handle, right? When doing this change, right, the energy associated with this change is given as minus 197 kilojoules mole. The R value was given, right? For this reaction, the reaction R was minus 197, right? That means you can write that on the top of the reaction arrow as well. For the second one, it was a SO3 gas. When that guy react with H2O liquid to produce the H2SO4 liquid, the reaction R of this reaction is given as 130 kilojoules mole. So these are the data provided there. So with use of these, you're supposed to find this thing, right? You're supposed to find this thing, right? This is your goal. This is your goal, right? These are the data provided. These are the data provided, right? With use of these data, you're supposed to find the enthalpy change of formation of H2SO4 liquid, right? Okay, let's try to solve this thing. Let's try to solve this thing, right? Okay, so what is the first thing to do when constructing a thermodynamic cycle? So I'm going with the thermodynamic cycle, right? We can use thermodynamic cycles to solve any kind of question, right? So that is the basics. That is the fundamental of solving problems, right? Thermodynamic cycle. So I'm going with the fundamental to solve this one. So when constructing a thermodynamic cycle, right, the first thing to do is what? The first thing to do is coming up with the goal, right? Coming up with the goal. Let's comes up with the goal, right? So the goal is this. Let's coming up with the thermodynamic equation, the balanced thermodynamic equation related to the goal, right? So that is all about the formation of H2SO4 liquid, right? So let's write that stuff, right? So it's all about formation of H2SO4 liquid, right? H2SO4 liquid. So formation means you have to start with what? You start with the reference forms of the constituent elements. So you have hydrogen there, so its reference form is what? Hydrogen's reference form is H2 gas. You have two hydrogens, so two hydrogens are represented by this form, right? And you have sulfur there. Sulfur's reference form is sulfur solid rhombic. You need one sulfur atom. Yes, it is one represented, right? And then oxygens. Oxygen's reference form is O2 gas. O2 gas. Right? You need 4 oxygens, so need some 2 here for the balancing. So you need to find out the enthalpy change of this. That is our goal, right? Okay. Right. Now the solving part. Right? Now you have to construct a thermodynamic cycle to solve this one. So Lamai, when data are given in terms of equations as well, data are given in terms of equations here as well, right? When such data are given in terms of equations as well, first use those things. After that, you can use the data given in symbols. First, use the data given as equations. That is the way of solving this stuff, right? That is the easiest way of solving this stuff, right? Okay. So I'm going to use these two equations first to build up my thermochemical cycle, right? Okay. First see these equations. First see these equations and see whether anyone here appearing with these equations, or whether, right, any of these equations coming up with any component which you have already written, right? Okay. So when examining that, you clearly see, right, this H2SO4 stuff, this H2SO4 liquid, that thing is appearing here as well. H2SO4 liquid is appearing here as well as here. So you can relate this equation to there. You can relate this equation to there. So what you are supposed to do is just take this equation out from here. Just take this equation out from here and bring this thing and paste that H2SO4 at here. Just bring this equation out from here and take this H2SO4 and paste it here. Then what will happen? Right? Bringing this thing out and taking this thing and just paste the H2SO4 here. Then you will observe something like this. H2O liquid is there, that thing is there, and the other side of the equation, represents what? The other side of the equation represents SO3 gas and H2O liquid. SO3 gas and H2O liquid. See, this is your equation, right? H2SO4, right? I have written the wrong way, the arrow, creation arrow, right? Just bring this out from here and just paste that thing here. So this change means SO3 gas plus H2O liquid giving you the H2SO4 liquid, right? Just copy this stuff or bring this stuff and paste the H2SO4 here, the common one here, right? Okay. So what will be the value for this energy change? It is minus 130 kilojoules per mole. Minus 130 kilojoules per mole, right? If you apply minus 130 kilojoules per mole of energy change to this system, this state of the system, that will be totally converted to here. That is what this equation says. So I have, right, used this equation. The usage of this equation is done now. No longer I am not going to use this thing, right? It is done. Okay. Now the next task. Now let's use the next equation, right? Let's use the next equation, right? Okay, do I have a different color there? So yes, let's see. So let's try to connect the next equation. You have SO3 gas and H2O liquid here, but with this second equation you have 2 of SO2 gas, 2 of SO2 gas. Sorry, and 2 of SO3 gas as well. So here SO3 gas is appearing, right? So just try to paste some SO3 gas to here from this equation, right? So here 1 SO3 gas is available. So here 2 SO3 gases are available. So just divide all the equation by 2. Just divide all the equation by 2. Just divide by 2. Even this energy value, divide by 2. Then what will happen? This thing will cancel off, this becomes half, and this thing will cancel off, and you will come up with some 1 mole of SO3 gas, some 1 mole of SO3 gas. Right now? Okay, then take that thing out and paste that SO3 to here. Take that thing out and paste that SO3 to here. Then what will it looks like? So SO3 gas is there. So on top of the reaction arrow, it will be 197 over 2 kilojoules per mole. At the other side of the arrow, SO2 gas and half of O2 gas will appear, right? SO2 gas and half of O2 gas will appear. Right now, that is just this equation, right? So that is this equation, right? So this thing is also written, right? That is this. So just applying this equation to here. But remember, you haven't done anything to this H2O liquid, right? So that H2O liquid still stands there. That H2O liquid still stands there. Nothing happened. By this energy change, only SO3 gas is produced by these things. So for the mass balance, and as nothing happened to the H2O liquid, that H2O liquid should appear here as well. Right now? So that is your usage of that first equation to construction of the enthalpy diagram. Right now? As by this energy change, only these two are connected here. As this state is appearing with H2O liquid, that H2O liquid should be there as well, as nothing has done to the H2O liquid, right? Okay, next, now it's time to convert this to here, So actually, that can be done by the combustions, See, this is all about combustion of H2 gas and combustion of sulfur rhombic, no? Combustion of H2 gas will give you the hydrogen oxide. Combustion of sulfur solid rhombic will give you the oxide of sulfur. So this is all about the combustion of H2 gas and the sulfur solid rhombic, right? So here we need to combust just 1 mole of H2 gas and 1 mole of sulfur solid rhombic, right? Okay. So to combust 1 mole of H2 gas, you need 286 kilojoules mole of energy, minus 286 kilojoules mole of energy needed to combust 1 mole of H2 gas to come up with the H2O liquid, and to combust 1 mole of sulfur to form the SO2 gas, you need minus 2898 kilojoules mole. By doing these two energy changes, or by doing this net energy change, you can completely convert these two guys to respective oxides. The other unreacted oxygens will appear here to form one H2 molecule and one SO2 molecule. 3 of oxygens will be used. Altogether here you have 4 oxygens. 3 is used to form the oxides. The other half, other oxygen, the half of O2 will appear unreacted, right now. So this is your thermochemical cycle. Done. Right. Now use the Hayes law to come up with the required delta value. Right. So Hayes' law. Right. So you have to come up with the initial and final states, right? So what is the initial and what is the final? So the initial state is this thing where all the arrow starts. Final state is this thing where all the arrows ends. Right? Initial to final, 2 routes are there. This is the straight route, this is the other route. Right? Okay. So enthalpy change in the first route, the deviation F, is equal to the total enthalpy change of the second route, right? This whole route, right? Okay. Right. So let's add these values. Minus 286, right? Minus 298 plus this value 197 divided by 2 is just, is that a positive value or negative value, right? it's a minus, no? Yes, it's also a minus value, right? So minus 197 divided by 2, it is going to be 98.5, no? This is also minus value, right? This summation, right? Right, no? Let's come up with the summation. So you can complete the stuff while I am doing the simplification, right? Right, it is 812.5. The value is 812.5. It's a minus value, right? Right, no? So just complete the stuff now. Right, no? So that is all we need to know about the combustion enthalpy and the related questions. Let's discuss about the next enthalpy term, which is going to be the standard enthalpy change of bond dissociation, right? Let's move to that. Right, a standard enthalpy change of bond dissociation. Now we are supposed to discuss, right? Bond dissociation. Right, it is known as deltation or dissociation, right? So let's discuss about this deltation or D thing, right? Change of bond dissociation. With that term dissociation, they have symbolized this thing, deltation or D, right? Okay, the first thing to do, as usual, let's come up with the definition, right? Let's come up with the definition of the bond dissociation enthalpy, right? After that, we can discuss the important stuff to, right, concentrate there, right? First, come up with the definition. At this space given, just write, right? Come to red color and write. Enthalpy change when one moles of bonds of a gaseous element / compound, 1 mole of bonds of a gaseous element / compound. Again, I am telling you, enthalpy change when 1 mole of a gaseous compound / element / compound, 1 mole of a gaseous element / compound undergoes dissociation undergoes dissociation to give gaseous atoms, to give gaseous atoms, to give gaseous atoms in the standard state, in the standard state. Right? Okay, just highlight the most important stuff there. Then we have the one more stands and what are the things at the other side? Those are the important stuff. No? Just highlight the important stuff there. First highlight like this phrase, right? 1 mole of bonds of a gaseous element slash compound. Just highlight that phrase. 1 mole of bonds of a gaseous element slash compound. So the 1 mole is with actually gaseous bonds. 1 mole of bonds of a gaseous compound slash element, element slash compound. That means 1 mole of gaseous element, like 1 mole of gaseous bonds are considered here. It's about bond dissociation enthalpy. So bond dissociation, so 1 mole of bonds, but remember those should be at the gaseous state. That is also important to note that 1 mole of gaseous bonds to be broken. And what are the things at the other side of the equation? Just highlight that stuff as well. To give gaseous atoms, to give gaseous atoms, the other side of the equation, to give gaseous atoms, right? Okay, let's come up with some examples here, right? Just box the definition, right? So let's discuss the examples appearing in your tute, right? So what are the examples there? Right, few examples are given. See, standard enthalpy change for bond dissociation of H2 is given as plus 436 kilojoules per mole. Right. So second example, there is standard enthalpy change of bond dissociation of O2, no, is given as plus 498, no? Yes. Let's write the whole tree and let's after that we'll discuss. Right. Let's come up with the related thermochemical equations for these things. Right? Okay. Let's come up with the related thermochemical equations, right? So where the 1 mole stands? So 1 mole stands with this species, right? Bond dissociation of H2 gas. Right? H2, bond dissociation of H2. So remember, it's about bond enthalpy. 1 mole should stand with bonds, but with gaseous bonds, right? Remember that. This is also important to keep that in mind, right? Okay, let's start with that. So it's all about like this. So you are supposed to break 1 mole of these gaseous bonds, 1 mole of bonds in the gaseous, right, element slash compound. So it's the elemental form here. It's important to note that this is going to be a gaseous. The compound or the stuff which you are going to break the bonds should be at the gaseous state. Without that, you can't apply the bond dissociation, right? So that will break to give you gaseous atoms. Give you gaseous atoms. That is very important, na? Gaseous state is very important. So if you have to break this bond, you will produce 2 of gaseous atoms, right? So this is where the one more thing stands, right? So 2 of gaseous atoms will be produced, right? So will give you gaseous atoms. That are things at the other side of the equation, right? So this value is plus 436. Right now? Okay. Let's come up with the next one. For the O2, the bond dissociation enthalpy is given as 498 kilojoules mole. So the bonds to break should be at the gaseous form, gaseous state, and this is the where the one more stands. Don't think this one has 2 moles of bonds. No, this is just a 1 mole of a double bond, 1 mole of a double bond, 1 mole of double bonds, 1 mole of double bonds. That is how we look at that thing. When producing gaseous atoms, basically this is considered as 1 mole of double bond, right? Okay, if you break that thing, you will produce 2 of oxygen gaseous atoms. So gaseous atoms should be formed. This is the definition, right? So the enthalpy change there is what? Plus 498 kilojoules mole. To break 1 mole of these bonds, 498 kilojoules of heat should be absorbed. Next one, for HCl. Not only for elements like this, but also for compounds, you can apply the bond dissociation enthalpy change. So anyway, again it should be all about gaseous bonds to break, right? This is where the 1 mole stand, right? If you break this 1 mole of bonds at the HCl, now you will form 2 kinds of atoms. As this is a compound, more than 1 kind of atoms will be produced. So if you break this bond, you will produce 1 hydrogen and 1 chlorine, right? Okay. And then those should be also at the gaseous state. Gaseous atoms are the products. So what is the value here? The value associated with this thing is plus 3431 kilojoules mole. Right now? When you are breaking 1 mole of gaseous HCl bonds, 1 mole of gaseous HCl bonds, 431 kilojoules of heat will be absorbed. Right now? So things are clear. So just complete these things, and then we will discuss about the mean bond dissociation enthalpy. First, just complete these ones. Right, no? Okay. So after that, let's discuss about the mean or average bond dissociation enthalpy. What that means? See, what that means, the average bond dissociation enthalpy. So all of these are about breaking of just one mole of bonds to come up with gaseous atoms. The species is totally converted to monoatomic gaseous species by just breaking 1 mole of gaseous bonds. That is what we have discussed so far, right? But when we have compounds, right, which are actually polyatomic, not the diatomic, but polyatomic, like CH4, like NH3, like H2O. Polyatomic means normally when you are with more than 2 atoms. If one atom is there, monoatomic. 2 atoms are there, diatomic. More than 2, normally we refer them as polyatomic. So when the compounds are with polyatomic form, polyatomic compounds are considered. To come up with, right, individual atoms, right, we have to break more than 1 bond. Like in CH4, to come up with that carbon gas and 4 of hydrogen gas atoms, we need to break 4 number of CH bonds. When it comes to NH3, right, as it is with 3 of NH bonds, we have to break all those 3 of NH bonds to come up with the nitrogen gas and 3 of H gas atoms. So in such situations, we will consider the average bond dissociation enthalpy. Let's discuss about that thing. So the example given in your note is about the CH4. With that, let's try to understand the idea, the total concept of mean or average bond dissociation enthalpy. Right? The thing written there is mean or average, right, standard enthalpy change of bond dissociation of CH4 is, right, given as 470. Lama, it should be plus 470, right? It should be plus 470 kilojoules per mole. Just do the change, right? Do that correction. Right? All the bond dissociations are endothermic, Lama. All the bond dissociations are endothermic. To break the bonds, you need to absorb heat. The bond should absorb energy from the surrounding to break that thing. To break a bond, you have to provide energy towards the bond. So that means bond need to absorb energy to break, right? So all the bond breakings are endothermic. All the bond breakings are endothermic. Delta H values are positive. Remember that. On the other hand, all the bond formings are exothermic. When you form the bonds, the energies will release. All the bond formings are exothermic. Delta H value is kind of a negative for the bond formings, but for bond breakings, always those are coming up as positive values, right? Bond formings are positive endothermic, right? Okay, let's discuss about this thing. Right, Lamai? So this is about CH4, bond dissociation. So when we have to write the CH4, you see CH4, it's a compound which is with multiple bonds, which is with actually more than 1 bond, more than 2 bonds. So CH4 is a compound with actually 4 moles of CH bonds are appearing there. 4 moles of CH bonds are appearing. Not just 1. 4 moles of CH bonds are appearing. So by a bond dissociation, you are always expected to come up with monoatomic gaseous species, individual gaseous atoms. So to come up with that form, monoatomic gaseous species, that means individual gaseous atoms like this, monoatomic gaseous forms, right? Gaseous atoms. Then you need to break 4 of CH bonds. You need to break 4 of CH bonds, not 1 but 4 of CH bonds. So this says to break 1 mole of CH bonds. To break 1 mole of CH bonds, you need to apply 417 kilojoules per mole. So 417 kilojoules per mole will be applied to break 1 mole of CH bonds, but you need to break 4 of CH bonds to come up with that state. So you need to multiply this thing with 4. You need to multiply this thing with 4. So that is going to be your energy change. I like that thing, right? 417 kilojoules per mole into 4. Here the kilojoules per mole value is per 1 gaseous bond to break. This is all about bond dissociation enthalpy. So 1 mole appears with the bonds, not with the compounds. 1 mole appears with the bonds to break bond dissociation. So to break 1 mole of CH bonds, you need 417. The CH bonds are the things appearing with the CH4. No? So to break 1 mole of CH bonds, you need 470 kilojoules of heat. But to come up as monoatomic species, right? Totally you have to break 4 moles of CH bonds. So that this thing should be multiplied by 4. This value is referred to as the average bond dissociation enthalpy. This value is referred to as the average or mean bond dissociation enthalpy. Right? So one can write this as 4 into delta H naught D. Right? So this 417 value is referred to as average bond dissociation enthalpy. Why is that? Why it is referred to as an average? Right? What is the meaning of that thing? What is the meaning of that term average? The thing is like this, Lamai. Right? So do you think that all of these bonds need the same energy to break? Yes, if you are to break it at the first time, yes, that is true. But it's like this, Lamai. The first bond breakage or bond breaking of the first bond happens with CH4, right? The bond breaking of first bond happens when CH4 is there from the CH4 gas. So breaking a bond from this needs some energy, okay, needs some energy. This is the first bond to break. But after breaking the first bond, the second bond to break will happen from this kind of a species. After they are breaking this bond like this, right? The second bond to break will happen from this kind of a species. So actually, this species is somewhat electron deficient compared to this one. This one is with the octet. This carbon is with the octet, but this carbon is lack of octet. Right? So this is kind of a electron deficient species, not like here. So this carbon is more keen of electrons, keen towards electrons. So this carbon is not keen to get rid of electrons. By breaking a bond, that is what happens. By breaking a bond, the hydrogen goes with its electron. So the carbon will lose one of the electron now going in its valence shell. So this guy is with only 7 electrons. This is with 8 electrons altogether. Just 7 electrons. So you need more energy to do this kind of harder process. As this carbon refuses to break the bond to release the hydrogen with the electron, you need to apply more and more energy to break that bond. If someone is refusing to do something, you need to provide more and more energy to do that process. That is the idea. So this need some great energy than here for the CH bond dissociation. By releasing the second bond, your carbon, let's say you release the second bond here, your carbon appears like this, which is even more lack of the octet, even more electron deficient, octet deficient. That means to break this bond, this one require more energy than this. So you have to apply more energy. So so these three bond dissociations need three different values, 3 different kilojoules mole values to dissociate those bonds, right? But for the fourth one, that will be easily released, Lamai. That will be easily released. So already, right? Most of the guys have been released now, so the carbon will leave the remaining one easily. Not keen of the bonds now, carbon, right? As all the guys are going, right? Carbon will release the ultimate one as well. You also go, no worries, like that. So this will be easily released, right? Anyway, these 4 bond breakings coming up with 4 different values, 4 different kilojoules mole values. So that we need to take some average to represent some rational value for all the 4 bonds. That is this value. Right? That is what is referred to as an average value. If you have few different values, taking the sum of all of these values and dividing it by the number of entities will give you the average value. That is will be a rational value. Some general value can be used for all the bonds. That is the idea of the average now. So that is used here, right? It's like this now. So average value is actually the total value divided by the number of entities. So what happens if number of entities multiplied by the average value? If number of entities are to be multiplied by the average value, then you get the total value, right? So that is what have been done here. The average value is multiplied by the number of entities, number of bonds, so that you get the total energy needed to break all of these bonds to come up as individual gaseous atoms. The thing is clear, no? What we need is the total energy needed, no? To convert this state to this, right? That can be done by taking the average value and multiply it by the number of bonds, right? That is what they have done, right? So you can write this stuff here at this space provided, right? Right, so here we can write this term as well. Here delta H naught D is an average value. Right, is the average standard bond enthalpy. Sorry, is the average value, or is the standard, just like that. This is the standard. The average standard. Dissociation enthalpy. Average standard bond enthalpy for 1 mole of CH bonds. then CH4 gas. Right now, write that thing as well. All right. Okay. So let's do the exercises appearing in page number 24. Let's do the exercises there. So 5 of the things are given. Let's come up with those things. This is clear? Right. So I'm going to do the question 5 to 9 in page number 24, right? What are the species given there? So as 5, you are supposed to write the thermochemical reaction for the enthalpy range of this thing. Actually, that is for the condition of CO2, no? Right? It's about bond dissociation of CO2. Sixth one is bond dissociation of H2O. 7, bond dissociation of NH3. Right? 8, bond dissociation of CH3OH. And finally, they're asking you to come up with the thermal equation for bond dissociation of CH3COH, no? Right. Let's try to write the related thermal equations. First for these one, right? CO2. CO2 is also coming up with more than one, right? Bond to break, right? Always you need to come up with the gaseous form. So when regarding the bond dissociation enthalpies, right? So by breaking all of these bonds, you will come up with 1 of carbon gas plus 2 of oxygen gas atoms. Always by a bond dissociation, we are supposed to come up with gaseous atoms, right? Monoatomic forms, right? So actually, this change means it is all about, right, 2 of delta H naught D's of C double bond O bonds. So to completely convert this thing to here, you need to break 2 of C double bond O bonds. Right now? Okay, let's copy this one as well. This is about H2O. So as you are referring to bond dissociation, you have to break the bonds in a gaseous compound or element. So H2O should appear as a gas if you are considering a bond dissociation, right? So by bond dissociation, you are supposed to come up with monoatomic gaseous form. So 2 of H gas plus oxygen gas, monoatomic gaseous forms, right? So to convert this into the monoatomic gaseous form, how many number of bonds should be broken? How many OH bonds should be broken? When it comes to H2O, see, with H2O you are with 2 OH bonds. To totally convert this into 2 of hydrogen atoms and 1 oxygen atom, you need to break 2 of OH bonds, right? 2 of OH bonds. Knowing the structure is very important, right? Knowing the structure is very important when applying the detection of D values, right? For this thing, NH3. So NH3 appear like this. So NH3 also should compass the gaseous form if you are considering bond dissociation. So bond dissociation involves only the gaseous states. All the terms appearing with the bond dissociation belongs to the gaseous state. If you have to come up with the monoatomic forms, that will give you 1 nitrogen atom and 3 of hydrogen atoms. So what is the enthalpy change needed here? You need to break 3 of NH bonds. So you need to apply 3 times the bond dissociation enthalpy of NH, the average bond dissociation enthalpy of NH, right? Clear? Let's come up with this thing. CH3OH is this kind of a compound. CH3OH. So we have to come up with the gaseous form if you are considering bond dissociation. Right? Gaseous bonds are broken, right? So the compound or the species should be at the gaseous state. So you are supposed to come up with monoatomic gaseous ions, right? Gaseous atoms, right? So 1, 2, 3, 4. 4 hydrogens, 1 carbon and 1 oxygen. No? 1 carbon at the gaseous state, 4 hydrogens at the gaseous state, and 1 oxygen at the gaseous state. Those are going to be the products, as is the bond dissociation, right? So what are the bonds to be broken, right? You need to break 1, 2, 3. 3 CH bonds. So 3 into bond dissociation of enthalpy of CH bonds, and 1 CO bond. So need to apply dissociation enthalpy of CO bond, and 1 OH bond as well to be broken, right? So delta H naught D OH bond, that need change also should be applied to break all the bonds to come up as 1 carbon atom, 4 gaseous hydrogen atoms, and 1 gaseous oxygen atom, right? Okay. So for this one, first of all, let's come up with the structure, right? So basically, you have to come up with the structure with the gaseous form as bond dissociations are considered, right? So to come up with the respective monoatomic gaseous atoms, that means 2 of carbon gas things, 1, 2, 3, 4 of hydrogen gas, and 1 of oxygen. To come up with this state, you need to break all of these bonds. That means 1, 2, 3, 4. 4 of carbon hydrogen bonds to be broken, single bonds, and 1 of carbon carbon bond dissociation enthalpy should be applied, and 1 of carbon oxygen double bond, it is also needed to be broken, right? That energy change should be also applied to break that bond as well, right? So this is going to be the total energy change you should be done to convert this state of the system to this state, right now? Okay, so complete this stuff, Lama. Then we'll move to the next section. Right, no? Okay, so let's move towards the problem solving, right? With the use of, right, delta H naught D values, right? So when thinking of problem solving with the use of delta H naught D values, right? So again with this enthalpy term, there is an equation available. There is an equation available, right? With the delta H naught F values as well, we had an equation, right? Delta H naught F values, like delta H naught R, the intervention of reaction is equal to delta H naught F of products minus the reactants, no? Such kind of a reaction, such kind of a Equation was there. Like that, we have an equation for delta H dot R in terms of delta H dot D's as well. This is delta H dot D's as well, right? What is that equation? First of all, I'll write the equation. At the end of this lesson, I'll derive that as well, right? So the equation is this. This can also be derived with the use of a thermodynamic cycle, right? As in the earlier case, right? We have derived the same thing with the use of the thermodynamic cycle with the delta F thing as well. So delta R is equal to, okay, right, the summation of bond dissociations of bonds breaking minus the summation of, this means the summation, right, bond dissociations of bonds forming, right? So this equation right, will give you the delta H R. If you know the delta D values of all the bonds associated with your components in your chemical reaction, if you know the delta D values of all the bonds with your components of your chemical reaction, then you can use this equation to come up with delta H R, right? Okay, so at the note is written there. Let's go to that. It is said enthalpy change of formation, enthalpy of reaction can be found out using the following equation. So you can write this thing, and there it is said to use this equation to find out delta H R, delta D values of all the bonds of reactants as well as products involved in the reaction should be known. With that, if the question fulfills that requirement, then you can use this thing, right? Then the next question is, what are these bonds breaking and what are the these bonds forming? Let's discuss about those things. What are these bonds breaking? I consider as these bonds to break. What are the bonds to form in your chemical reaction? So you should have some idea about that thing to apply this equation. So when we are thinking of a chemical reaction, right, we say a chemical reaction occurs by first breaking all the bonds of the reactants, to come up with individual gaseous atoms, and then those will recombine to form the products. In such a manner, a reaction will occur. We'll assume like that. So if you want to know something like this, see, let's say you are with this compound CH4 and you are reacting with O2 to come up with CO2 and some H2O, right, like this, see, right, to these two happen, right? If you think of this reaction, right, we can assume first all of these bonds, this case is phase reaction, right, we can assume first all things should be in the gaseous form, right, to apply this thing, right. We can assume first all of these bonds will break, to form individual atoms, that means 1 carbon gas and 4 hydrogen gas plus 2 of oxygen atoms, sorry, 3 of oxygen atoms. First, all of these things will break like this by applying the delta D values of these things, right? Of what? Reactants of the reaction, right? And then these bonds will form. These bonds will form. The bonds of the products will form, right? So if you think of in this manner, this is about, right, products. These are products. So relation to R plus products is equal to reactants. Relation to R plus products is equal to reactants. Relation to R is equal to reactants minus products. That is a very special equation. So bonds breaking are the ones at the reactant side, and bonds forming are the ones at the product side. So normally we assume first all the bonds of the reactants will break and those will form to form the products. All the reactants, all the bonds in the reactant side will break. That is why bonds breaking that term is used, and then those things will form. Those things will rearrange to form the bonds in the products. Rearrange to form the bonds in products. So bonds forming appears at the product side, and bonds breaking appear at the reactant side. That is how the equation came. Right? Clear, no? So that is the idea. Right? Okay? Clear? Right. So let's use this equation to solve few questions. So we can use this equation, right, to solve problems, right? Or we can go for thermodynamic cycle as well. So there are two methods available to find out the delta to R with use of delta to D values, right? You can use this equation as well as, if you need, you can come up with the thermodynamic cycle as well. Thermodynamic cycle is the fundamental number. You can use that thing to solve for any kind of problem, right? Okay. So first of all, let's try to solve a question with the use of this thing. If you can solve the question with the use of the equation, just solve with the use of equation, right? That is the easiest way, you know. If kind of equation is not available to solve the question, then go for the thermodynamic cycle, right? Okay, right. Let's come up with this first question, which is appearing on the page number 24, right? We are supposed to solve that thing with the both forms, with the use of equation as well as with the use of a thermodynamic cycle too. First we'll go with the equation, right? Okay, so what is the reaction there? The reaction is this, right? This is the reaction available. So 1, 2, 3, 4, 5 carbons are there, no? 5 carbons are there, and these are the hydrogens appearing. Double bond is there and triple bond is there, no? Some hydrogen here. Gaseous this thing reacting with 3 of H2 gas to give you this gaseous species, no? So keep that in mind. To apply the equation, this equation, all the things should be at the gaseous form, right? Gaseous state. If not, you can't apply the bond dissociation things, right? Delta D values can be applied only if you are supposed to break the gaseous bonds, right? This is delta R need to find, right? Okay. What are the data given? So some data are given with some bonds, right? D values of few things are given, CH, CZ, CZ double, HH single, what else, CZ single, and even they have given you the D value of CC triple as well. It is also appearing there, right? And the values are 413. These are positive values, right? Right. What is 413? Then 610. Then you have 435. So I'll write here. And then you have 346, and finally you have it 835. No? Yes, those are the values appearing there. Those are the data provided. Right? Okay, let's solve this thing with the use of equation first. Right? Let's solve this with the use of equation. Right? That is first thing, right? Using equation. Right? Okay, let's apply the equation. So first thing, applying the equation, coming up with the correct equation, that is this, right? Delta H naught R is equal to delta H naught D of breaking bonds. Just write like this, that is enough. No need of writing the sigma always, right? No need of writing sigma always, and no need of bonds thing. D breaking, that is okay. Breaking bonds minus delta H naught D forming bonds. Keep that in mind with this equation, right? It is the bonds at the reactant side minus the bonds at the product side, right? It is very important. Normally, when taking a change, we first take the final minus initial. This final minus initial will give you the changes in science. But it's a very special occasion where the things at the reactant side, the initial side, minus the things at the product side, final side. Special, no? Keep that in mind. There is only one equation like that in our LSUs, right? Okay. So apply this one. Apply the numbers now. Substitute numbers, right? Bonds breaking. What are bonds breaking here? So you have 1, 2, 3, 4, 5, 6. 6 CH bonds. 6 into CH bonds. CH bond carry 413. 6 into 413. 6 pH bonds to be broken. Bonds breaking, right? Bonds breaking appears at the reactant side. And 1 CC bond, that is 1 CC single bond, right? That is 346 plus 1 CC double, 1 CC triple. That is 610 plus 1 CC triple, 835 plus, that's all with this compound here. That is all with this compound, and 3 of HH things, no? 3 of HH modes. 3 into HH. That value is 435. These are the bonds to break at the reactant side. Sorry, reactant side, yeah. Minus the bonds to break at the product side, right? Let's write the stuff. So you have 1, 2, 3, 4, 5, 10, 12. No? 12 into CH bonds. That means 413 plus 1, 2, 3, 4. 4 into CC bonds, CC single bonds, right? That is 346 plus, that's all. Yeah, that's all. So that is about bonds to form all are as kilojoules mole. Unity is essential. Substitute with the correct units. Let's come up with the answer then. It's very easy to solve these kind of questions with the use of equation, right? So actually 6 into 413 is there, 2 into 413 is there. So all of these will cancel off as minus value, right? This becomes 6. 4 into 346 is there, right? Here you have 2, no? Sorry for that. 2 CH bonds, no? 2 into 346 is there here, right? Right? 2 into 346 is there. And here 1, 2, 3, 4. 4 into 346 is there. So this will cancel off. And 2 will appear here. So now simplify the numbers. So you can write these things while I am simplifying. Right, okay. So this side 610 is there, 835 is there, and 3 into 435. Right, 3 into 435, no? Yeah, it's there. And with the other side, you have 6 into 413, right? And then minus 2 into 346. So the number is minus 420 kilojoules mole. Right, no? That is the number. Right? Okay. So that is how we are supposed to solve this equation, solve this problem with the use of equation. It's very easy, right? Just delete d values of bonds breaking minus bonds forming. Breaking bonds are available at the reactant side, and the bonds to form are available at the product side. Right now? Just complete this stuff now. Make complete correct. So have this kg mole minus 1 value as well, right? So substitution should be done with the SI units, right? Okay. Right. This is how we are supposed to solve this kind of question with the use of equation, right? So then let's solve this one with the use of thermodynamic cycle as well. It is not hard, right? Now we are very familiar with the thermodynamic cycles. Let's see how to solve this thing with the use of thermodynamic cycle, right? Okay. Let's try to solve this thing with the thermodynamic cycle, right? So it's part B, no? Solving with the use of a thermochemical cycle. Right? Okay. See how to construct here. Right. So what we need to come up is actually the immediate state now. right? So the problem is given now. So first thing to do when constructing a thermodynamic cycle is to come up with the thermodynamic reaction related to the goal, right? So this is the goal to find out. This is the goal which we are supposed to find out, right? This unit R. So just write that equation. Write the thermodynamic equation, right? So now we are supposed to come up with the thermodynamic cycle, right? So the next step to do when constructing a thermodynamic cycle is to come up with the imaginary state, no? To come up with the imaginary state. That is the next thing to do, no? Right. So what components should be there at the imaginary state? What components should be there at the imaginary state for this cycle here? For that, just look at the data given. Just look at the data given, right? All the data are given in terms of bond dissociations. So bond dissociations involve the respective compounds as well as the monoatomic forms, monoatomic gaseous forms. The respective compounds or the respective elements are already written in our diagram. But the monoatomic forms are not written in bond dissociations. Monoatomic gaseous forms are involved, but those are not written yet, not displayed in our diagram. So that your imaginary state should build up with the monoatomic forms, monoatomic gaseous forms of your system. So this system contains 5 carbon atoms and 12 hydrogen atoms. So just write 5 carbon gas atoms and 12 hydrogen gas atoms as your imaginary state. Right now? Got the idea, no? So 5 of carbon gases and 12 of hydrogen gases as the imaginary state. Now we can connect these states via energy changes. Let's connect the states via energy changes. So when it comes to bond dissociation, right, the reaction arrows are written towards the monoatomic gaseous states. So in bond dissociations, the compounds, we will break the gaseous bonds of the compounds to come up with gaseous monoatomic forms. So in bond dissociations, the reaction arrows are directed towards the monoatomic gaseous forms, right? This case as well, right? Let's try to connect this state to here. To come up with single atomic gaseous situation, monoatomic gaseous forms, you have to break all the bonds appearing with the state. So let's break all the bonds to come to this state. So we have it 1, 2, 3, 4, 5, 6 carbon hydrogen bonds to be broken, right? So let's write this stuff. 6 into carbon hydrogen bonds. So that is 413 kilojoules per mole. And you need to break 1, 2 of carbon bonds there. So carbon bond 346. What else? 1 of carbon double and 1 of carbon triple. Carbon double comes up with 610. Carbon triple comes up with 835. Not only that, you need to break 3 of HH bonds as well. 3 of HH bonds as well to completely convert the state of your system to this state. 3 of HH bonds. Those carrying 435 per 1 mole of bonds. Such 3 are needed. 3 bonds to be broken, right? Okay. If you have to apply all of this energy change, this state of the system will totally convert to this form, right? What about this side? To convert this state of the system to totally to here, you need to break 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 CH bonds and 5 CC bonds. So not defined of 4 CC bonds. To break one of CH bonds, you need 413 kilojoules of heat, but you need such 12 CH bonds to break. So to that 12 into 413 kilojoules mole. To break one CC bond, you need this kind of energy in 346, but now you need to break 4 of CC bonds to come up with the monoatomic forms, gaseous, right? So that is 346 now into 4, as 4 moles should be broken. So that is energy enthalpy cycle or the thermochemical cycle. Now you can apply the Hayes law to come up with the final solution, right? To apply the Hayes law, first you need to come up with the initial and the final states. So this is going to be the initial state where all the arrow starts, and this is going to be the final state. Sorry, yeah, this is going to be the final state where all the arrows ends, right? By considering these initial and final states, let's apply the Hayes law. Let's apply the Hayes law, right? So I'll apply the Hayes law here, right? At the top, I'll apply this Hayes law, right? So there are two routes to start from the initial to come towards the final. This is one route, and this is the second route, right? So the enthalpy change of those two routes will be the same. That is what Hayes law says, right? So delta H naught R plus this, that is the total enthalpy change of first route, right? The 4 into this enthalpy change of first route, total enthalpy change of first route will be equal to the total enthalpy change of second route, right? So equal to 6 into 413 plus 2 into 346 plus 610 plus 835 plus you have 3 into 435. This is the total in the change of second root. So if you have to simplify this stuff, right? So this will cancel off, 6 here. So this will cancel off, become 2 here, right? And you can bring this thing to the other side, and you can subject the delta to R. If you subject delta to R, you will get the same value as in earlier. Both the solving techniques should give you the same value, right? The value we have obtained last time was 420. That value should come from this problem solving method as well, right? Okay, so that is how we are supposed to solve with the use of a thermochemical cycle here, right? Okay, just complete this stuff here now. So actually you have 2 more questions appearing at the page 25. So just do them at home, right? Things are now clear. So I have solved with the use of the equation as well as with the use of the thermochemical cycle here, right? So there are 2 equations, 2 questions appearing at the page 25. You can solve those things at home, right? I'll send you the answers to your group, right? So just solve it right now. Okay, then with this, that is all we need to know about the delta D values, the bond dissociation enthalpies, right? So with this, we'll wind up for today's session, and next day we'll start with the atomization enthalpy, right? A new term, and much work to do with the next class, right? Let's see. Then goodbye. See you next week.